Hi guys, this video is going to talk about the StarGAN algorithm, which allows us to carry out multi-domain image-to-image translations. An image-to-image translation essentially means changing an attribute of an image, like changing someone's hair color from black to blonde, or changing a man to a woman. Just to clear out some terminologies, in this video, attribute refers to features in an image such as hair color, gender, or age. Attribute value is a value for a specific attribute, for example, black for hair color, male for gender. Domain is a set of images having the same attribute value, like people with blonde hair or people smiling. GAN, or Generative Adversarial Networks, is an approach that does really well on image translations. GAN consists of two parts, a generator and a discriminator. A generator generates fake images while a discriminator decides or discriminates whether the generated images are fake or not. An image produced by the generator is acceptable only if considered real by the discriminator. Thus, the generator and discriminator are always in a cat-and-mouse race where the generator tries to fool the discriminator and the discriminator tries to catch fake images fed to it. Although GAN performs really well, it has its constraints. For each translation, we need to train a pair of generator and discriminator. For example, we need one pair for changing an image from male to female, and another pair for changing it from female to male. This is really inefficient when changing multiple attributes in an image. There are other algorithms such as pix-to-pix, unit, cycleGAN that can perform image translations. However, they all share the same problem as GAN. We need a separate model for each pair of domains. StarGAN is a new and improved approach for handling multiple attribute translation. StarGAN only uses a single pair of generator and discriminator. StarGAN can also learn from multiple datasets that have different attributes at the same time. For example, it can learn to translate hair color and facial expressions at the same time, where one dataset consists of different hair color and the other consists of different facial expressions. StarGAN has the best performance in multiple attribute translation, comparing to existing approaches. It can also learn from multiple datasets using only one pair of generator and discriminator. StarGAN is a more convenient, more efficient image translation approach with better performance. Now let's see how StarGAN actually works on a more granular level. This image explains the working of StarGAN pretty well. There are three basic processes that make up the StarGAN algorithm: the generator, the discriminator, and the reconstructor. Let's see how they work. The first is the generator. Let's say we have an image of a sad boy here and we want to make him happy. We first feed the image into the generator's neural network. The generator downscales the original image into a lower resolution. The pixels in this downscaled image act as single neurons in the network. The hidden layers in the neural net then identify the facial features of the boy and modify the pixels that need to make him smile. Now this generated image is fed into a discriminator, which assesses whether this image is real or fake, and also computes the class of this image. So if the discriminator thinks the image is real and also thinks the boy is smiling, we have an acceptable image. Otherwise, the generator has to do a better job. The generated image is also transformed back to the old image to see how different the reconstructed image is from the original image. This helps us identify how much the algorithm is distorting our original image. The general idea is that we generate an image that is real enough to fake the discriminator so that we don't have an awkward looking smile or something that doesn't look very natural. Something that actually represents the target domain so that the boy actually looks like he's smiling, and something that's not very different from our original image so that it retains its original content and we don't get a distorted image as our output. The loss function in the StarGAN algorithm has three different parts that addresses these three ideas. The first part is the adversarial loss. In this equation, d source of x is a value between 0 and 1 that signifies how real the discriminator thinks x is, with 1 signifying x is 100% real and 0 signifying x is 100% fake. A quick analysis of this equation will show you that the discriminator needs to maximize this function to make sure it identifies a real image x as real, i.e. d source of x should be as close to 1 as possible, and identifies a fake image g generated by the generator as fake, i.e. d source of g should be as close to 0 as possible. On the other hand, the generator will try to minimize the function to fool the discriminator into thinking that the generated image g is real and belongs to the class C. The second loss is the domain classification loss. The goal of our algorithm is not only to create a realistic image, but also to classify it into its target domain C. Thus, the discriminator tries to minimize this function to make sure it classifies a real image X into its class C dash, and the generator tries to minimize the second function to make sure the discriminator classifies a generated image G into the target domain C. Minimizing the adversarial loss and the domain class loss does not guarantee that translated images preserve the content of its input images. In this equation, G is a generated image with class C, and G of G, C dash constructs an image that goes back to the original class C dash, or you can say that it reconstructs the original image. Here we want the old image minus the reconstructed image to be as low as possible, thus the generator seeks to minimize this loss function. Here are the complete loss functions for the discriminator and the generator that they both seek to minimize. Here the lambda CLS and lambda REC are hyperparameters that control the relative importance of domain classification and reconstruction losses. There is a problem when we use multiple datasets with StarGAN. Label information is only partially known to each dataset. In the case of Celeb A and RAFT, while the former contains labels for attributes such as hair, color, and gender, it does not have any labels for facial expressions, such as happy and angry, and vice versa for the latter. So how do we solve this problem? To alleviate this problem, we introduce a mask vector M that allows StarGAN to ignore unspecified labels and focus on the explicitly known label provided by a particular dataset only. In StarGAN, we use an n-dimensional one-hot vector to represent the mask vector, n here being the number of datasets. We define a unified version of the label as a vector C, where Ci represents a vector for the labels of the ith dataset. One important question is, how do we know how good or bad StarGAN is performing? We choose some baseline models for comparison. We went on to adopt DIAT, CycleGAN, and ICGAN. DIAT uses an adversarial loss function to learn the mapping like StarGAN does. How can we adopt a new architecture with regularization? This method has a regularization term on the mapping as x minus f to preserve identity features of the source image, where f is a feature extractor pre-trained on a facial recognition task. The second baseline model is CycleGAN. Similar to StarGAN, CycleGAN uses an adversarial loss function. However, they regularize the mapping differently, which is by using cycle consistency losses. As you can see, the biggest difference is that this method requires two generators and discriminators for each pair of two different domains. The third and final model used for comparison is ICGAN. It is simply another network architecture which combines an encoder with the CGAN model. Now, a natural question that follows is, what is a CGAN model? CGAN learns the mapping Z, C to X that generates an image X conditioned on both the latent vector Z and the conditional vector C. In addition to the CGAN model, ICGAN also uses an encoder to learn the inverse mappings of CGAN, EZX to Z and ECX to C. But why? This allows ICGAN to synthesize images by only changing the conditional vector and preserving the latent vector. The first resulting set is made using the Celeb Faces dataset. This dataset includes a lot of celebrity images, and they are used to train the model. Here are a few photos that we generated from our analysis. Most of the images look pretty realistic. However, there are some anomalies. For example, in the fourth column in the left image, there's a man wearing sunglasses. The sunglasses get distorted as we perform the translation, especially when we change the hair color from black to blonde. Therefore, although StarGAN works pretty well in a general scenario, it might not work in certain cases. For example, if someone is wearing some accessories like a hat or sunglasses or something like that. Here's a comparison of StarGAN's performance with some of the baseline models we explained before. These stats come from a voting competition that the authors held. For every generated image, each participant had to vote for which category the image belongs to. And as seen in this table, StarGAN got the highest performance among the four methods. In the second test, they generated images with multiple change attributes, and again, StarGAN got the highest performance among the four methods. RAFT is the second dataset being used. RAFT images contain only a small size of samples in each domain. DIAT and ScycleGAN can only use 1,000 training images at a time, but StarGAN can use 4,000 in total. Here's the table comparing the 4 baseline models using the RAFT dataset. 90% of the data in the datasets was used in the training set and the remaining 10% was used in the test sets. Using the ResNet 18 convolutional neural network architecture, the StarGAN algorithm was able to produce over 99% accuracy. Here is an example of image translation using both the StarGAN and RAFT dataset. The upper row only uses the RAFT dataset and the lower row uses both datasets. The bottom row seems to perform better by using more datasets. Thank you very much for watching the video. We hope you got a basic understanding of the StarGAN algorithm and an appreciation for its relevance in the machine learning world.